So, oops, it's stuck. Okay. So we have here 4 root x. Do you remember what we need to do to get the derivative here? Yeah, what do we do?
Just need to change the square root of x.
To power a half.
Yeah.
So then the derivative would be 4 times a half times x to the minus a half. So that's 2x to the minus a half. And that's fine, that's the first derivative. But what we're going to look at next is something called the second derivative, which means we differentiate again. So I'm going to scroll down. So this here is the second derivative, and its definition, its formula, so to speak, is just the derivative twice on your function. So for example, in the one I just did, the second, hey, come on. So if I differentiate this one again, I get the second derivative. So for example, here, in my example I'm doing, the second derivative would mean the power comes down again, so that would be 2 multiplied minus a half, and then you subtract 1 again from the power, so that would be minus 1 and a half. So 3 over 2. So that's called the second derivative. And we'll look at the meaning of it now. So just write that down so far.
Are we going to do something with acceleration, displacement, and speed?
We will later, yes. In fact, did you miss the maths class yesterday? You did.
Yeah.
And I actually mentioned that point in that class. Okay. So let's have a look at what exactly the second derivative means. So let's take a graph here. Window, 12 vertically. Okay, let me just delete that. So let's take a cubic, for example. X cubed plus x squared plus 5x plus 1. Just some random cubic as an example. Okay. Whoops. Zoom out. You know what? Actually, let's make it as our first example. Let's make it a little easier by just making it a quadratic instead. X squared plus 5x plus 9. Okay, so drawing that and reset. Zoom down a bit. Okay. Hey, come on. The same. Now this is y here, and the
No case. Yes, no case.
Mohammed, come on. So here, this is the y, and what does the derivative represent here? The slope of the tangent. So what I'm going to do is I'm going to draw the tangent at a couple of places. We'll draw it first at -6 here. Okay. Tangent of that at -6. And I'll graph that after I get it. Graph and graph. Come on. And graph. There's that -6. Now I'll do it at -4. Tangent of that at -4. You can try and draw this as well if you can. It'll help to explain the second derivative. So there it is at -4, and then we'll do a couple more. Tangent, I'll do -2 and then 0. -2. And graph that one. Graph, and then lastly, let's do 0. Tangent of my equation when x is 0. Okay, so we can't quite see that. So my first tangent when x is minus 4, what was the slope of that line? Well, we had it here actually, you can see it. My first one I drew was minus 7. Then for my second tangent line, what's the slope? There it is there, isn't it? 1. And then for the third tangent line, and so on and so on. So what I'm doing here is, you need to try and use your imagination of the tangent is moving along the curve, and you can see its slope is changing. Yeah. So what if we draw a graph like this, where on the x-axis is x, but on the y-axis is the value of the tangent, its slope. So if I have minus 6, what was it? I think it was minus 7, wasn't it? And then it's still negative here. But what happens when I pass minus 3? The slope is now positive. So if I graph this, when it's negative, it was negative. And then when it was positive, and it switched at, what would I say, minus 3 about, was it? So that means it's 0 here. Yeah, so I'd say the graph of the tangent line looks like this. When it was negative, it was negative. When it was at minus 3, it was 0. And then past minus 3, it was positive number for the slope. Now this makes sense as well, because if I have a quadratic, whatever, I don't remember, whatever the quadratic was, what is the derivative here? 2x plus 5. Now, if I have a cubic, what type of graph would I get for its derivative? A quadratic. Okay. Let's have a look at the cubic one now. Okay, so just delete this. Yeah.
The first derivative, we find the tangent of the curve, the slope of the tangent, right?
Yeah.
For the second derivative, what are we finding?
But that's what I'm going to try and show with the cubic, what it represents exactly. So we'll take a cubic. Let's say this cubic here that has the roots at 1, 2, and 3. Expand. So there's my cubic, and let's graph that one. Okay, good. That's better. Okay, so let's have a look at the derivative. What is the slope here? Positive, negative, 0, what would we say? Positive, and then here, 0, and then here, negative, and then here, 0, and here, positive. So it goes positive, 0, negative. Let me graph that. So here we are. Okay, so it starts off with positive, and then what's next? 0, and then what's next? Negative. And then if I go back here, negative, and then 0, whoops, 0, and then positive. So you'll get, this type of graph. But of course you expected that, because the derivative of a cubic is a quadratic, and in fact we can get it right here. What's the derivative here? 3x squared minus 12x plus 11. There it is there. And that's exactly the graph I was trying to draw. So I'm going to delete this graph and then now look at this quadratic here. So that's what I was trying to draw. But now what's interesting is this point here. This one here, where the derivative graph has a 0 tangent slope here. What does that represent on the original cubic? Well, if I put the cubic back in now, put them on top of each other, can you see what's special about the point where the derivative is also, the derivative has a derivative of 0? What's special about the original blue curve? Well, that's just a coincidence here, but something else at that point.
Coincide at the point where dy dx.
Yeah, well, it's where the y dx has what?
0?
Not 0, because 0 dy dx is at the top and the bottom. So dy dx isn't 0 here. Now, look dy dx positive, negative, or 0? Positive. Here, 0 here, negative here, 0. Now, is this a max or a min? Minimum. And this is a maximum. So here is a hill, and then here's a valley, and this point right in the middle here is where it's switched. So this is where we need to have two new words to describe a curve like this, and then a curve like this. And you can see the first one is a hill shape, and then the second one then is a valley shape. And the point at which it changes from being this type of shape to this type of shape, you can find that by finding when the second derivative is 0. So what we have so far is when the first derivative is 0, what does that give me? It gives me the turning points, the max and min. When the second derivative is 0, it gives me something called the inflection point, when it changes from being a hill to a valley. So I'll write that down now. So second derivative, here's the result. So if the second derivative is 0, that's called inflection point. Actually, I think that's actually an x, but I'm not so sure. Inflection point. And that's, in other words, the point at which the graph changes from being a valley shape to a hill shape. But these also have some meaning as well. This has a meaning, and this has a meaning as well. When the when the second derivative is negative, this means the graph has a hill shape at that part. So it looks like this.
Maximum and minimum.
It's related to that, yeah. If you calculate the second derivative at all of these points, it'll be negative. The name of this shape is concave. If you calculate the second derivative at these points, you'll get a positive number when the shape is convex. And if you calculate the second derivative at a place in between the two shapes, that is when it'll be 0.
And this is for a cubic.
And in fact, it is for any graph. The cubic was the one I did as an example. So in other words, when the graph has a negative second derivative, its shape should be some kind of hill shape. And when it has a positive second derivative, its shape should be some kind of valley shape.
What about the quadratic? Because when you found the second derivative, it's a straight line.
Now that's interesting, yeah. So let's take a simple quadratic we can do in our head. X squared plus x plus 1. What's the derivative of x squared plus x plus 1? 2x plus 1. And what's the derivative again? 2. That's positive. So what shape is that?
Concave.
And is it that shape? No, but the original, the quadratic is that shape.
Yeah.
That's what the second derivative tells you, the shape of the original.
Oh, yeah.
Yeah. Now, what was the second derivative for my quadratic? 2, wasn't it? Is it always 2? Yeah, it's always 2. It's not 2x, it's 2. So the quadratic is always this shape. But now what we'll do is we'll look at a cubic, because a cubic changes, doesn't it, from maybe this type of shape to this type of shape. So its second derivative will switch from being positive to being negative or something like this. So we'll do some examples now. Okay? But this is the basic idea. It's all there. We're using the second derivative to tell us more about the shape. So let's have a look at some examples. So in number 1, I just ask you to calculate the second derivative. I'll skip that and go straight to number 2, which is use the second derivatives to find maximum and minimums. So I'll just go straight to the cubic one I want to do. Y equals 2x cubed minus 3x squared minus 36x plus 36. This is 2f. So as a small exercise now, I want you to give me the stationary points here, from like the last lesson. Find the stationary points, okay? So do that now. And I'll graph it as well as you're working on it. This is 2f, 2f. 2f, yes. It's just 2f.
Do I get the second derivative as well?
No, just give me the stationary points. Yeah. Yes, yes.
Y equals 0 as stationary point.
No, that's the root.
That's the
When's the stationary point? I give you a clue. You did it half an hour ago. Got them? So did you get something like maybe roughly minus 2 and 3 for the x's?
minus 3.
Minus 2 and 3.
Minus 2 and 3. And then the y is maybe something like, looks like about 75 and minus 50 or something? Good, okay. There's the, by the way, there's the graph of it up there, okay? So you can see which of the 2 points is the maximum. Which x value is the maximum? When x is minus 2. But of course, if you don't have the graph, you don't know this. But you do know here the second derivative should be positive or negative. If it's a maximum, it should be negative. And if it's a minimum, it should be positive. So let's have a look at that now. It's like that, yes. Yeah.
So we define the second one.
So, well, first let me just quickly do the first part. 6x squared minus 6x minus 36 equals 0. X equals minus 2 or 3, was it? Yeah. All right. Now, that is the first derivative. Now let's find the second derivative. It is 12x minus 6. If I put minus 2 in, what do I get? I get minus 24 minus 6. What's that? It's negative. Yes. And if I put 3 in, I get 36 minus 6, which is positive. So at the place of 3, it's a positive second derivative, which means it has this type of shape. And at the place of minus 2, it has a negative second derivative, which means it has this type of shape. Which makes me think that the minus 2 answer is the maximum, and then the 3 answer is the minimum. And I still have to find the y, but that's easy to do because all I have to do is take my 2 answers and put them back in. So I'd like you just to do that now for me. Give me the y values as well, please. Oh yeah, you gave it to me already, didn't you? It's 80 and minus 45.
In the book it's different.
Is it?
Yeah, it's minus 2 and 65.
2, which is this? 2. Oh well. 2f. Some mistake there.
Minus 45, no, it's right.
No, it says 65. It should have been, what did you say? 80. Yeah, so the first one is just wrong then.
Okay.
Well, I assume that you all get 80 for it, yeah? Yeah. So I'll just change that. Yes.
Could we just
believe this? I said earlier today, didn't I earlier today, someone will later say, why do I need to do this? Can't I just look at the Y value?
Visions.
So why can't you just look at the Y value? Because there are some examples, like maybe a log what I did earlier today. Yeah. See, I know what people are going to say, and even when I try to say, no, don't say this, it happens. Okay, so this is quite common in the exam. They'll give you a cubic, and they'll ask you to find the max or the min. So that's how you do it. First, you get the first derivative, you make it equal to 0. Then, you get the second derivative to check if it's positive or negative. Now, I should also point out that if the second derivative is equal to 0, what does that mean here?
It's a straight line.
No.
Point of
It could be.
in between the
Doesn't change.
Yeah, now see, it's a bit strange, isn't it? If we have 0, we don't know if it's a max or a min. Okay? Now, I just said a minute ago, 0 means it's changing from being a max to a min. Right? But when you find the slope of the tangent to be 0, that's usually at the top, not when it's changing. So how could it be that the first and the second derivative is 0? Like, that doesn't make any sense. And that's sometimes happens. And I'll give you one simple example which you can all do now, which is x cubed. Okay, so let's take x cubed. What's the derivative? 3x squared. When does that equal 0? When x is 0. Now what's the derivative of 3x squared? 6x. Yes? If I put x as 0, what do I get? 0. So the first derivative is 0 and the second derivative is 0, which means it's a turning point. You remember turning point, and it's changing from a max and a min. So that's weird. How can it be a turning point and changing from a max and a min? Well, if we look at the graph, we can kind of see what happens. So if I just draw x cubed, okay. Now I'll zoom in a bit to help. So this is what's happening with x cubed. You can see this type of shape. Is it a hill shape? What is it? Hill or a valley shape? It's kind of a hill shape. Yeah, concave. And then this one here is concave. So it is changing. So here is 0. But you can also see on the graph, if I draw a tangent line there, it'll be flat as well. In fact, when you look at this graph, it almost looks like a flat line already at 0. So this is a special case as an example of when the first and the second derivative is both 0. Okay? When this happens, there's a special name for this. When the first derivative is 0 and the second derivative is 0, because you have some shape like this, it's called a saddle point. Saddle. Yes. Yes. Now listen, just be careful. Just because the first derivative and the second derivative equals 0 doesn't mean you'll get this. It could still be a hill shape. Okay? So what I'm trying to summarize here is the following, which you can make note of. If the second derivative is 0, it means there's two possibilities. The first possibility is you have this type of shape. So that's the two possibilities. You have this type of shape, or it's not a problem and basically this technique has failed. Yes?
What's the second one?
Yeah. The second one means it's not this type of shape, that the technique has failed, meaning the method that you used did not work, but it still could be a max or a min. So in other words, it failed. The technique failed. Now, what does that mean? Is there any examples of that? And there are, but in my interpretation of the syllabus would seem to say that it's not really on the syllabus. And they did ask it 1 year. So when we're doing the past papers, and if we come across it, we'll look at it. but I think it's getting a bit too complicated to look at that. So it's enough to say right now, if the first derivative is positive, what shape is that? Its positive is convex, and negative is concave. And 0 means it's probably a saddle point like this. But in the exam, that won't happen. In the exam, when you try to check if it's a max or a min, it should be clearly positive or negative. So it's not something to worry about. So let's have a look at some more examples now. Right. Can you look at number 3? Can you look at number 3? Are you looking at it? 3. Stop. Okay. All right, so let's have a look at this. Guys, come on. So I'm going to, it's number 3, I'm going to graph it first. So we have 3x cubed, 3x cubed minus 9x squared plus 6x plus 5. All right, here's the graph. Whoops, a little too far. And a little too much. All right, if I look at this graph, where would you say the graph is concave? It looks like from minus infinity all the way up until...
6, 5?
No, just in the x direction, yeah? I'd say to about here, isn't it? Which I think might only just be about 1. And then what happens when it passes 1? It goes to convex shape. So let's calculate it exactly. Whoops. So if I want to know when is it convex, that means I want to know basically when is the second derivative positive or negative? Did I, sorry, I didn't, sorry, I said concave in the question, sorry. Concave,
Negative.
that means when the second derivative is negative. So let's calculate the second derivative. First derivative, 9x squared minus 18x plus 6. Second derivative, 18x minus 18. I would like to know when is 18x minus 18 less than 0. That is when x is less than 1. So the graph is concave when x is less than 1. And that's the answer.
Do we need to find the values of y?
No, I just want to know for what values of x will it be concave. Yeah, minus infinity to 1. So the answer at the back is written like this. When x is from minus infinity to 1 is when it's concave shape. Okay, let's have a look at number 5. Number 5. So number 5, I say, or ask, where is the inflection point for the function? So how do I find the inflection point? What equals 0? What equals 0? Second derivative equals 0. So first, let's get the first derivative of 3x cubed plus 9x squared minus 7x minus 5. It would be 9x squared plus 18x. That's the first derivative. And then the second derivative is 18x plus 18. I want to know when that is 0. That is when x equals minus 1. Sorry.
7.
Well, I don't think it's too much of a problem because even though I forgot the 7, it still goes on the Next line. So when does that equal 0? When x is minus 1. Let's find the y now, please. What's the y? Sub it in. Let's see, that'll be what is it? 8, thank you. So for this graph here, the inflection point is there at minus 1, 8. Okay. 15 now. Sorry, I'll give you a minute there. Can I go down 15?
So Stephen, number 3, do we have to substitute the 1?
No.
No.
Okay, 15 now. I want to know, when is this function increasing? And before I solve it, I'm going to just graph it. Minus x squared minus 14x minus 4. Okay, graph. Zoom a bit. What the? I must have typed something in wrong here. Hang on. That's right, isn't it? Yeah, okay.
Zoom out.
Zoom out. I didn't zoom out enough, huh? Okay, zooming out. Oh, there we go. Okay, so when is this function increasing? What would you say, looking at the graph? Minus infinity to, say about minus 10, huh? And then when it passes minus 10, it starts to decrease. So, how could I find out when is the function increasing? Something else. I mean, that would work, but I'm thinking of something else. Think of it as an inequality as well.
Find the second.
Not second? First. Yeah.
Oh, you can find the tangent.
Bigger than 0. Because what does dy dx mean? Slope of tangent. And if it's increasing, then the slope of the tangent should be positive. So you want to know when it has positive slope. That's what increasing means after all, positive slope. So we get the derivative and check when is it positive. So when x is smaller than minus 7, so from minus infinity to minus 7, what did we say? We went with minus 10. So it doesn't look too bad from the graph. So x will be increasing from minus infinity to minus 7. And then once it hits minus 7, it's at the maximum. And when it passes minus 7, it is decreasing. Yeah, now this is very important for the exam. There's always a question on this, every single exam. I cannot think of an exam where they've not asked for this, okay? It'll be in section B at least, and sometimes maybe in section A too, okay? So what I'd like you to try for me, from number 2, I'd like you to do one of each type. So a quadratic, a cubic, and a log, which actually looks like W, X, and Y. From number 2. I'd like you to also do number 4, number 6, number 11, and number 16. Did you make note of that, Joshua? Or are you just planning on remembering it? You're going to go home and forget about that, though. You're going to go home, did write it down. Are you sure? Positive. Charles, come back in, Joshua. You've got a trainer behind you, quite right. We have we don't have plan. Oh yeah, that actually reminds me. So tomorrow there's the extra maths class at 3 o'clock. and I actually had good attendance last Friday. What I'm going to do in the extra maths class tomorrow is I'm going to, now that we're nearly actually finished, because if you look at the book, how many lessons? We have 1, 2, 3, 4, 5. So in fact, we'll get the book finished next week. So I can start doing exam papers. So I'm going to do some exam papers in the double class tomorrow. Basically what will happen is, I'll take out the exam, it's 2-hour class tomorrow, and it's a 2-hour exam, so I'll be able to do at least one exam tomorrow.
Like a practice exam or also together?
No, I'll solve it on the board.
Can we come here this class?
No, this room's not free.
Invite only?
No, there's a group of people who have preference, and then everybody else is first come, first serve. So there's some reserved seats, and then the peasant class, it's first come, first serve. Yes?
We're going to have something like a practice exam before.
I'll give you a practice exam too.
Can I ask?
Joshua, you're packed up and you're continuing to pack up. Will you stop? Yeah, take your book, sir. Hang on. Wait for Joshua to take all his book, sir. Open. You'll need your maths book too. Maths book. Now, if you want to see a past exam, I'm going to do it tomorrow in the extra maths class. It's 2 hours long, but like I said, when I'm doing it on the board, it should be less than 2 hours. Okay, and I think there's 10 questions in section A. I should be able to do 9 of them. I can't do the 10th question because it's on the chapter for next week. And in section B, there are 6 questions, and again, I can do at least 4 or maybe 5, depending on what the topics are. Okay, so if you want to see a past exam, you should go to the class tomorrow. If you want to try it at home, it's on Moodle. At the bottom of the page is a link called Past Papers. It's a book of past papers, 1 paper from each year. Okay, I think I'll just start with the most recent paper in the book and then go backwards, okay? So like I said, if you really want to see that, if you feel you need to, make sure you're in the room early because the room is smaller than this.
Within me, I can be the first one there.
What's that?
Within me, like I can't try it at home, so.
Yeah, no, you're going tomorrow.
Yeah.
No, I said there are reserved seats. So you can have, I will have the front row blocked off. I'll have reserve written on it.
With the names?
With the names, yes. I'll have a little red robe. I can, you know, let them in. Yeah. And I can have a little flashlight as well. Oh. So don't worry, okay? You'll see it tomorrow. Right, so you were worried that you won't have there won't be space for it. I'll make space. Don't worry. Okay, so we'll leave it there. Make sure you try those, and it's a good idea if you print out the past exams so that if you do go tomorrow, you can look at them when you're doing them, okay? And there's a supportive book on Moodle as well, isn't there? Yeah, so.